But what I'd like to do is kind of sum up almost everything that we've talked about today around that idea of engineering and cost. One of the things that I really want to stress is that when you know the data semantic, you know the behavior. And when you know the behavior, you know the cost. And as soon as you know the cost, guess what? Now you're engineering. And that's what's beautiful about this language. Because the machine is our model, okay? The language allows us to look at code, understand the cost, get a good, reasonable idea how things are going to perform. But honestly, at a micro level, which is what we're talking about, it all is really around that behavior, at those data semantics. So let's take a look at some code here. Now, we're going to start with on line 10. We're defining a new type called data. Data's got two fields, name and age. And right underneath that data declaration, I've got two methods. Again, I'm mixing semantics because we're still learning mechanics here. Now, we've got a method named displayName, which is using the value semantic or value receiver there on line 16. We've got a method named setAge, which is using those pointer semantics or a pointer receiver. Now, as a side note, we do not write getters and setters in Go. If I'm doing a code review and I see any sort of method named set or get, I promise you the code review is going to stop. These are not APIs that provide something. We don't want APIs that just provide the user the ability to manipulate state. That is not a good API. Now you've got to write tests for these things. They're probably not even going to be used. I think these are bad programming practices that at least I was taught when learning object-oriented programming. We don't want to do these things in Go. So unless you don't want me to show up in front of your doorstep, don't be writing getters and setters here in Go. And that's the only reason I leave this method here in the code base, so I can have this conversation. Getters and setters are not an API. APIs must provide something, okay? And just changing state is not enough. Okay, so we've got our two methods, our pointer and our value semantic methods here. And we're going to jump into main. And right away in main, I'm showing you right there on line 29 inside the main function that we're going to be constructing a value of type data. So there it is. There's our data value, D, and it's got my name in there. There it is, Bill. It's got my name in there. And one of the first things that I want to show you is line 36 and 37. This is how we call methods, right? And again, Go's not in creating syntax here. We have the value dot behavior, D dot display name on line 36, D dot set age on line 37, value dot behavior. But remember something, technically all we really have in a program is state and that behavior through functions. We have our data and we have our functions. And there's no difference here. What I want to share with you first is the idea that a method is really syntactic sugar around a function call. That's why the compiler can also be very flexible around that receiver data and adjust to make the call. So if you are really making that call on line 36, D.displayName, or on line 37, D.setAge, what the compiler is really doing is what you see on line 42 and 43, and in a stack trace, that's really what you're going to see. You see on line 36, the method call to display name actually gets converted into a function call, which is named data.displayname, and that receiver parameter looks like a parameter because it really is, the first parameter. This is the same thing in your object-oriented programming languages with this and self. They are the first parameter of a function call. Now, we're not going to be calling methods like line 42 and 43. All right? If you start calling methods like that in your code and you say, Bill Kennedy showed me this, I'm going to throw you under the bus and say, I have no idea where that developer got this from. This is not how we call methods. We call methods like line 36 and 37. I'm showing you this for two reasons. One, to just again show you that methods are syntactic sugar behind actual function calls. And if you were to look at a stack trace, you would see the function call. That's where I got that syntax from, not the method call in its code form. All right? Now, we go back to our value of that data value right here, D, naming Bill. And we're still inside the function main. But I want to show you these 4 lines of code because, again, the whole idea is to start to understand cost. What is the cost of this code? And you can't do that unless you know behavior, and your data semantics are a big driver for understanding behavior. So if you look on line 52, we're assigning the method display name already bound to the D value to a new variable called f1. We are not making a method call. I want you to understand that there is no method call being made. Those 2 parentheses do not exist. We're actually doing an assignment. Now, f1 is a function variable. It's part of that family of reference types. And if we were to draw that up on the board, f1, just like channels and maps, are just pointers. And what does this pointer point to? Well, this pointer is going to point currently to an internal data structure that looks like this, a 2-word data structure. Now, the first word is going to be a pointer to the code for, in this case, display name, right? Because this data here, it has 2 methods. It has that display name method, right? And it has that set age method. It has both of these. So that pointer is going to point to the implementation, the real implementation for display name. And the other problem is, because at the end of the day, we want to do what's on line 55. I want to have an indirect call to d.displayName through the f1 variable. The whole point here is the indirection, right? That's where decoupling comes from. Decoupling comes from indirection. That's what gives us that flexibility. And the f1 is indirectly going to be able to execute behavior against D, right? Through that pointer. That's what we're trying to get to. So now we have a pointer to the actual implementation for display name, but what about the data? You cannot call display name without data. Well, let's go back and remind ourselves about display name. Display name is a method. Display name is using a value receiver, which means it's using value semantics. And what are the rules on value semantics? The rules are that every piece of code operates on its own copy of the data. We're trying to get that isolation, right? We're trying to get all of that integrity, all of that goodness. So what does that mean for f1? Well, if display name is saying that we have to use value semantics, in other words, everybody has to get their own copy, well, that has to also be extended to the f1 variable. And that's exactly what's going to happen. So now the second word here is going to point to a copy of D. It's got to have its own copy because the data semantic at play is value semantics. Do you see how now this is really coming into play? Because we know value semantics are at play, we know a copy of D has to be made and stored specifically with the f1 variable, which now means that when we call 55, line 55, we are going to call the display name method, but it's going to be called against our copy of D, which now means on line 58, when we change Bill to be Joan, and we call f1 again on line 61, we're not going to see the change. Because anytime we call display name through the f1 variable, we're going to be operating on our own copy. So this level of decoupling is coming from the indirection that we're setting up. But there's one more thing that's important here, and that is the other cost. Indirection is a cost. But the other cost here now is allocation. Think about it. This value now has to allocate because we've made a copy at runtime. Remember, one of the rules we have for values being on the stack is that if the compiler does not know the size of a value at compile time, it cannot be on the stack because frames are fixed at compile time. The size of a frame is defined at compile time. So if the compiler doesn't know the size of something at compile time, it can't be on our stack. The compiler can't know about this value at compile time because we're doing this copy at runtime. That means that has to be on the heap. So what we're learning right now is that when value semantics are at play and decoupling is being applied, that copy is going to be made, and that's going to cost us not just the indirection, but an allocation as well. All right, let's look at using setAge now in the same scenario. Here, we're going to assign set age to the variable f2. So let's go ahead and do that. Here's f2 right here. f2 is going to have a pointer also to that two-word data structure. We know that this pointer is going to point to that code. Again, in this case, it's going to be the code for set age. And what happens here? Well, set age is using pointer semantics. And what does pointer semantics mean? It means shared access. So we're not going to make a copy in this case. This pointer now gets to point to the original value. Interesting. So now what does that mean? It means on line 73, when we call F2, what's going to happen is we're going to see Joan, right? We would see Joan. We're operating against this right here. Now on line 76, what happens? Well, we're going to change that to Sammy. Would we be able to see Sammy on that call? Yeah, we would, because we're sharing the original data. That's the whole idea of the pointer semantic. We would see the change. Now, the question becomes, since all of this code is on the frame for the main function call, right, all within that one box, right, the reality here is that all of this code that we've been working on, if this is our stack, right, is all in here. D is in here. All of our code is operating within this right here. Our Go routine is right here. Does that mean now, since we are sharing D and all of the code is isolated in this frame, does D have to allocate? And the answer is no, it doesn't have to allocate, because it's not being shared in such a way that it has to come off the frame. But there are flaws in escape analysis, unfortunately. And one of those flaws is that when there is double indirection to data, and in this case there is, because when we make that call, we're going to have double indirection to the data, the compiler says, unfortunately, I can't track it anymore through static code analysis, and that has to now end up on the heap. So the cost of decoupling, and it's not just in Go, but this is the language we're working with right now. The cost of decoupling is always allocation and indirection, regardless of the data semantic that we're working with. We have to remember that. So if you need the most blazing fast Go program that ever existed, you can't be decoupling that code, because even that one allocation on the heap is going to cause the garbage collector to have to come in and do some work. And we already talked about the latencies behind that. So you have to remember this. Now, the reality is that we don't need the most blazing Go software ever, right? We need things to be fast enough. And we want that allocation to happen if it's going to make our life better, especially around that multi-threaded software development. So this is not a big deal, but I want you to be able to start reading code. I want you to be able to understand that, hey, I expect to see that in a profile. There's going to be an allocation there. And you know what? That's a productive allocation. Decoupling can create those productive allocations. But if you're decoupling for the sake of it, and this is going to occur with our interfaces as well, as we're going to see very soon. So if you're using interfaces for the sake of using interfaces, and now you've got that level of decoupling, and now you're allocating and there's no real value behind it, that's that non-productive allocation that I don't want to take. So I always want to be engineering. I always want to make sure that we know what the cost of things are. I always want to make sure as a team we agree that we're willing to take these costs because these things are more important. And decoupling is going to be incredibly important for us to be able to maintain very large programs on large teams. We're going to take these allocations. That's going to be fine. I just want to know that we are, and I want to know as a team that we're okay with it. So this is decoupling through the use of a function-based reference type right here. And you're seeing, again, whether we're using our value or pointer semantics, now we understand behavior and we understand cost.